So yeah, this research is from my doctoral research under the supervision of Professor Nader Aly, which includes both numerical and experimental work, which was done also in collaboration with the industry. So to give it a sense of practicality in terms of applications and so on. So this will be the outline of my presentation. I'll first start with a brief introduction of what is reinforced masonry, the applications, and so on, and then quick overview of previous research and what are the challenges and limitations that are facing this type of building system, and what are the objectives of our research that was done and how we achieved those objectives, like the methodology of this research. And then I will go over the experimental work, the numerical work, and conclude with some design recommendations that were taken from this combined experimental numerical work. So first of all, masonry is one of the most ancient construction materials. It's not a relatively new type of material. Reinforced masonry is an alternative construction material that is successfully utilized in multi-story buildings, but in regions with low seismic hazards, such as in Winnipeg, they went up to 24 stories, and also in Brazil, they went to up to 20 stories. So it's already utilized, but in regions with low seismicity. So multi-story reinforced masonry buildings is not something that is scarce, but it is limited to some regions. And probably this is because of many challenges that is facing this system when it comes to applications in moderate and high seismic hazard regions. So quick overview of previous research. So when it comes to reinforced masonry as a construction system or a building system, masonry shear walls are the most common seismic force resisting elements. So in the literature, many researchers were trying to incorporate confinement to the end zones, because as you know, incorporating confinement would enhance the compressive strains and so on. So that would improve the lateral performance of these walls in terms of displacement and resistance. So this is the typical rectangular configuration of reinforced masonry shear walls, and you would see that. Change the pointer. So in a typical wall, it's typically a rectangular configuration with masonry blocks filled with grout in the reinforced cells, where it has a vertical reinforcement. Some of the cells won't be having reinforcement, but it would be grouted, because this type of masonry construction is called fully grouted, because all cells are grouted with horizontal reinforcement, and the fifth shell is typically this. And some of the researchers like Priestley and Elder looked at inserting confinement plates in the end zones, like the extreme ends, to enhance the ultimate displacement capacity of these cross sections. That was okay in enhancing that, but it did not solve one of the main issues that I'll describe after going over the next type of confining as well. By Snook et al., they put confining materials such as fiber, polymers, and so on, to enhance the ductility and displacement capacity. Now, these two options, or these two alternatives to enhance the compressive strain is okay in terms of that, but we still have an issue of lateral stability, because we have a single layer of vertical rebars, and in a cyclic lateral loading due to earthquakes and so on, we have these bars could be susceptible to buckling, and once they buckle, they cause the face shell to spool, and then we start losing the lateral stability of the wall. So in 2010, Shear et al. Proposed using two masonry blocks, and with this configuration, we have a thicker end zone where we can put two layers of vertical reinforcement, and that would probably enhance this lateral stability issues, because we now have a confining hoop to the end zone. And this is a summary of the previously tested walls with boundary elements, which is this configuration. And we only have 12 of them, so we have a very limited number in the literature, with the highest aspect ratio of 3.23 and a highest compressive stress of 9.8%. So then it's clear that we need more testing to look at more parameters for challenges and limitations for this type of construction. First, next slide. Okay, so we have a limited applications, as mentioned earlier, for moderate and high seismicity regions, and this is probably because of the limited research on this type of construction, because many previous earthquakes, like we've seen that in masonry, there's a significant amount of damage, but that was not actually reinforced masonry. It's typically unreinforced, and it is taken as a perception that this is masonry in general. After that, the use of the load-bearing wall system, because typically in masonry buildings, we have the walls resisting all the vertical and lateral loads together, which puts the walls under a limited ductility because of the increase in the axial load. And the use of conventional walls, as I explained previously, for the rectangular configurations, we have a lateral stability issues when these extreme rebars start to buckle and causes the face shield to spool. And we also have limitations in the available research. The best configuration that I mentioned was having the two masonry blocks to have a multi-layer of reinforcement in the end zone. However, this configuration is also restrictive when it comes to sizing this boundary element and also spacing the transverse reinforcement. So we need a better solution. So also, when we look at the recent MBCC, there was an addition of a ductile type of masonry shear walls, which was given a higher ductility related response modification factor, reflecting the potential with this type of construction. However, it was assigned the same building height limits of the moderately ductile shear wall. So the moderate ductile shear wall, which had an RD of 2, was having the same height limits of the ductile walls, which had a ductility factor of 3. And this is probably due to the limited research and the relatively new system. Like this type of construction was recently added in the 2015, the ductile type. So more research would be required to emphasize the enhanced performance of this type of masonry shear wall. So this brings in the objectives of this research, which was first to develop component and system level solutions, and so in terms of design and detailing recommendations. So at the component level, we propose to utilize C-shaped masonry blocks instead of the stretcher blocks, and this would give more rooms in terms of sizing the boundary elements and arranging different layers of vertical reinforcement and also spacing of transverse reinforcement. It will also allow having a uniform grout core. And this enhanced component will be integrated to a proposed structural system having two types of masonry shear walls, ductile walls, resisting all the lateral loads and part of the gravity loads, and gravity walls only resisting vertical loads and would be isolated from the lateral resistance by utilizing separation joints and limiting the lateral resistance. Like in terms of the lateral stiffness would be limited as such that they don't attract any or minimal amount of the lateral force. And with this enhanced component and system, we'll be able to propose building height limits that are more representative to the ductile type of masonry shear walls, especially when utilizing boundary elements. And that would be integrated into buildings, and these buildings would be analyzed and studied to finally enhance the seismic performance and competitiveness of multi-story reinforced masonry shear wall buildings. So this is the overall objective, and this is the methodology that we utilized to achieve those objectives. So the methodology had two research axes, like experimental and numerical. Both of them were parallel and they interact with each other. So the experimental started with testing of 6 reinforced masonry shear walls with boundary elements with different design and detailing parameters to quantify the structural performance at the component level. And then we use this to validate a numerical model, which was also validated against existing masonry shear walls with boundary elements in the literature, which was already limited as mentioned earlier. And then with that, we proposed the hybrid structural system, which is composed of ductile and gravity walls, and quantified the system level seismic performance using a standard methodology given by the Federal Emergency Management Agency of the US, which is P695. And with that, it was possible to recommend building height limits by combining all those components to ultimately enhance the seismic performance and competitiveness of multi-story reinforced masonry shear wall buildings. So going over the experimental work, which had two phases. The first phase looked at the axial load and detailing effects, and the second phase looked at the in-plane cyclic response of masonry shear walls with boundary elements having different design parameters. So in this experimental work, 6 half-scale reinforced masonry shear walls with boundary elements were tested, and these walls actually were not the full specimen. So we looked at 12-story walls and 6-story walls, but only the plastic hinge region of these walls were tested in the laboratory. And to reduce the variability between the tested specimens, the construction was controlled using similar masonry blocks and grouting that was done in a controlled environment. And all the specimens were fully grouted and were frictional dominant, most probably because of the high axial, high aspect ratio, and because of the capacity design that was utilized in designing these test specimens. So this is the test matrix, which included 6 specimens starting from wall 7 to wall 12. And the reason it starts from wall 7 is because this is a continuation of another bigger research, which had another 6 walls by for another researcher. For the first 3 walls, this was for phase 1, which looked at the effects of the axial load and detailing, and the second 3 walls were used again with wall 7 as a reference for the in-plane cyclic response for different parameters, which will be explained in this slide here. So this is wall 7, which is the reference wall. It had this cross-section with 4 rebars in a boundary element that's 190 by 190, and it was a 12-story wall. For wall 8, it was identical in everything except that it had a higher vertical reinforcement ratio in the boundary element, and this was to investigate the effect of the vertical boundary element vertical reinforcement ratio on the response. And then comes wall 9, which was identical again, but only with larger boundary element having 8 rebars. So comparing this with wall 8 would quantify the effect of the boundary element size, and comparing it with the reference wall would allow quantifying both the effects of the boundary elements reinforcement and size, because this had a larger boundary element and higher vertical reinforcement ratio in the boundary element. So this was for phase 1. For phase 2, wall 7 was carried as the reference wall, and it was compared with wall 10, which was identical in everything except that it was a 6-story wall, so a shorter shear span to depth ratio of 4.4 compared to the 8.8 of the reference wall. And then this was to quantify the effect of the wall's shear span to depth ratio. For then wall 11 was compared with wall 7 to quantify the effect of the type of blocks. As mentioned earlier, like the conventional improvement was to use 2 stretcher blocks. So this specimen was added here to investigate what's the impact of using, whether it's the stretcher blocks, these blocks, or the C-shaped blocks. So those effects were studied by comparing wall 11 and wall 7. Finally, wall 7, again, the reference wall is compared with wall 12, which was identical. 2 walls were identical, so wall 7 and wall 12 were identical, except that wall 12 had lap spliced vertical rebars in the web at the foundation interface and at the first floor in the boundary elements. So the testing scheme had an applied top moment to compensate for the difference in height between the full specimen and the tested specimen, which is only the plastic hinge region. And for this, for the estimation of the top moment, a triangular lateral load distribution was assumed to correspond with the first mode shape. So on the tested specimen, first of all, the vertical compressive stress was applied following this loading protocol, which goes from 0 to 2.25 megapascal and stays constant throughout the testing. And this was to simulate the gravity loads. After that, lateral displacements were applied to the top of the specimen, and this followed this loading protocol, which had 2 phases, a pre-yield stage and a post-yield stage. The pre-yield stage was mainly to capture the first yield displacement and use it to construct the post-yield loading protocol, which was then made of multiples of the yield displacement that was found experimentally from the pre-yield stage. And then at each lateral displacement level, a corresponding top moment was applied to compensate again for the height between the tested specimen and the full specimen. This is the testing setup that was used, which had 3 double-acting hydraulic actuators, 2 vertical, 1 horizontal, and all of them were attached to a strong steel frame. The specimen had a bottom reinforced concrete footing representing a real footing for a wall, and a top loading beam representing a diaphragm, a rigid diaphragm, and an out-of-plane support system at the first floor level. So the footing, the bottom footing was fixed to the transfer footing, which was also fixed to the structural lab strong floor. The top specimen, the top footing was fixed with the vertical actuators to apply the top moment, and the lateral actuator, the horizontal actuator, was applying the lateral displacement. So out of plane displacements were restrained, but rotation was allowed because this specimen was subjected to lateral displacement. So lateral translation and rotation was allowed. Out of plane displacements were only restrained. For the instrumentations, we used LVDTs and potentiometers to monitor and record all the lateral, vertical, diagonal, sliding, and shear displacements. And also, internal strain gauges were mounted to capture the yield strain when it happens at the foundation wall interface, and also to monitor any strain penetration inside the footing and establish the strain profile over the height of the specimen. This video here shows the testing of wall 9, which had the largest boundary element with 8 rebars. And you see it now going to small displacements. You probably don't notice what's going on, but for larger displacement amplitudes, it will start to get obvious. And this here would show what's happening in the end zones, in the boundary elements. So up until 5 delta yield, there was no major damage, only cracking in the horizontal mainly direction, representing the flexural behavior of this specimen. And as it progresses, start to see the spalling of the face shell of the blocks here. And then the crushing of the grout core in this boundary element. The vertical rebar started to buckle once, and again it buckles again, third time, and it fractured here. So the failure was significant crushing in the grout core and the fracture of the vertical extreme rebar due to the low cycle fatigue effect. Looking at the hysteretic response of these tested specimens, wall 7, the reference wall, had a reasonable amount of energy dissipation capacity, failed at a ductility factor of 10 due to a flexural mode of failure, characterized at the end by crushing in the grout core and buckling of vertical rebars, and that happened at a ductility factor of 10. For wall 8, which had 8 rebars in the boundary element, there was a higher amount of energy dissipated. The failure was also at a ductility factor of 10 due to the crushing of grout core and buckling of the extreme vertical rebars. For wall 9, which had a larger boundary element, there was a higher amount of energy dissipated relative to the previous two walls. The failure was also ductile at a ductility factor of 11 due to crushing, and as you've seen in the video, crushing and the fracture of the extreme vertical rebar. For the wall with the shorter shear span to depth ratio, there was a reduction in the energy dissipation and the ductility, and there was more predominance from the shear cracking. It failed at a ductility factor of 8, also due to crushing in the grout core and buckling of vertical rebars. For wall 11, which had stretcher blocks in the boundary elements, the failure was at a ductility factor of 8. There was a reduction in the energy dissipation capacity, but it failed in the flexural mode due to crushing in the grout core as well and buckling of vertical rebars. Finally, wall 12, which had spliced vertical rebars, had a slightly limited energy dissipation capacity, failed at a ductility factor of 10. And interestingly, you can see there was no almost no cracking at the locations of flap splices due to the increased flexural resistance from doubling the vertical reinforcement. And the failure was not due to the bond failure, so that was prevented, which is a good enhancement in terms of performance of masonry shear wall especially. So there was no failure at the splice. The failure was crushing and buckling of vertical rebars. So quantifying the effects of these studied parameters, first of all, the effects of the boundary elements detailing to increasing the vertical reinforcement from this 4 bars, 8 bars, and then increasing the size of the boundary element. There was an increase in the lateral resistance going from wall 7 to wall 8, obviously because of the increase in the concentrated reinforcement. And there was also an increase in displacement at ultimate. And for this wall compared to that wall, only the increase in the size resulted in a slight increase in the lateral resistance of 5%, and in the ultimate displacement by 13%. For wall 9 compared to wall 7, the reference wall, there was a significant improvement in the ultimate resistance by 41% and 29% for the ultimate displacement. Looking at what happened with the ultimate compressive strains in the end, all the three walls had high values of compressive strains, much higher than the code value, which is the typical 0.0025. And that happened at a ductility factor ranging between 2 and 3. Wall 9 reached the highest compressive strains at all ductility levels, and wall 8 relative to wall 7 was much higher. So all of them were achieving much higher compressive strains, but relatively speaking, wall 9 was doing better than the other two specimens. And looking at the energy dissipation, the three walls had high energy dissipation, and this was calculated as the ratio between the dissipated energy and the input energy. The dissipated energy being the energy enclosed by the hysteretic loop, and the input energy being the area under the skeleton of that loop. And relatively speaking, wall 8, which had a concentrated reinforcement at the same ductility level, achieved a higher energy dissipation relative to the other two walls, which only had A3 bars, and wall 9, which had the larger boundary element with A3 bars, was having the highest energy dissipation ratio of 0.89. For the residual displacements, again, it emphasizes the amount of energy dissipated. At first yield, the walls had similar residual displacements, which went higher as the load was progressing. Walls 8 and 9 had much higher than wall 7, and at failure, the residual displacements were 24, 52, and 51 for walls 7, 8, and 9. So to conclude, from the first phase of testing, C-shaped blocks and the boundary elements allowed providing sufficient seismic detailing in the compression zones, gives more flexibility compared to the previous configuration with structural blocks. The lateral resistance is mostly affected by the increase in concentrated reinforcement in the boundary elements. Ultimate displacement can be enhanced by increasing the concentrated vertical reinforcement or the size of the boundary element. Displacement ductility can be improved by increasing both the size, mainly increasing the size of the boundary elements, because this gives more room for confinement and enhancing the ultimate compressive strain. Increasing the boundary elements concentrated vertical reinforcement and size increase the ultimate compressive strain, which increases the curvature ductility and hysteretic energy dissipation and equivalent viscous damping. Looking at the ductility related modification factor of those specimens, it was an average of 7.7 at peak load and 8.4 at ultimate displacement, which quite higher than the 3 value given in the code, reflecting this enhanced performance when using even the C-shaped blocks compared with the regular stretcher blocks. Finally, with sufficient end-zone detailing, the tested wall sustained high residual displacements, which again reflects the increased amount of energy dissipation capacity. For the second phase, the effect of shear span to depth ratio, the reduction from 12-story to 6-story from the shear span to depth ratio of 8.8 to 4.4 resulted in increasing the lateral stiffness by 86% and reduced the strain hardening. So the ratio between ultimate to yield was 1.27 for the tall wall and dropped to 1.16 for the shorter wall. And for wall 10, which had the shorter shear span to depth, shear span to depth ratio, there was more obvious or distinct degradation in the response. And there was also a reduction in the idealized displacement ductility by 61% at peak load and 15% at ultimate displacement. For the boundary elements block type, whether it's the C-shaped blocks or the stretcher blocks, both of them having exactly the same spacing of transverse ties and configuration of vertical rebars, there was a similar lateral stiffness and resistance. However, wall 7, which had C-shaped blocks, was having a hardening response, whereas the other wall had a degrading response. Wall 7 had a higher displacement capacity. The idealized displacement ductility of wall 7, which had the C-shaped blocks, was higher by 45% at the peak load and 27% at the ultimate displacement. For the effect of splicing, there was an increase in the initial stiffness by 93% and the stiffness at yield by 25%. There was a significant increase in the strength stiffness degradation by 40% when lap splices were present. There was no impact on lateral resistance, which means that the wall was capable of achieving the design capacity even though there was lap splices, which is a good enhancement in performance. And there was a slightly higher strength degradation. The ultimate displacement was lowered by 26%, but the idealized displacement ductility was lowered by 35% at peak load and 7% at ultimate displacement. For the shear and flexural displacements, all the specimens had a flexural dominated response with more than 80% of the top displacement due to flexural component, except for wall 10, which had the reduced shear span to depth ratio that resulted in an increase of the shear displacements by 65%. So final conclusions from the component level is that the walls demonstrated a ductile response dominated by flexure. The reduction in the shear span to depth ratio increased the lateral stiffness and resistance. It increased the rate of stiffness and strength degradation. It increased the contribution of the shear mechanism. It lowered the displacement ductility by 61% at peak load and 15% at ultimate displacement. And the use of C-shaped blocks in lieu of the stretcher blocks improved the construction process time and quality. It had a minor impact on the cracking pattern, initial stiffness, lateral resistance, and stiffness degradation, and also the energy dissipation capacity. It increased, so C-shaped blocks in lieu of the stretcher blocks increased the displacement ductility by 45% at peak load and 27% at ultimate displacement. For the lap splices, For the lap splices, the vertical rebars in the plastic hinge, so the presence of lap splices affected the cracking pattern. It increased the lateral stiffness. It had a negligible impact on the lateral resistance and increased the rate of stiffness and strength degradation. It also lowered the displacement ductility by 35% at peak load and 7% at ultimate displacement. It also slightly reduced the energy dissipation capacity. However, with the proper design of the splice and the presence of sufficient confinement, the impact was controlled and the bond failure, most importantly in the tensile reinforcement, was prevented. An overview of the numerical work, which also had two phases. First phase, looking at the performance of this type of construction in buildings and what is the possible height limits when utilizing this category of walls with boundary elements. And this was achieved by studying 6 archetype buildings having different number of stories located in 2 regions, Montreal and Vancouver, to represent moderate and high seismicities. And we looked at total heights that exceeded the height limit given to this category of masonry shear walls, which was actually the height limit of the moderate ductile system. And a structural system was proposed as mentioned in objectives, like it had 2 types of walls, gravity and ductile walls. Gravity walls resisting only gravity forces, and ductile walls resisting both lateral loads and vertical forces from the gravity loads. And then a macro modeling approach was developed in Seismostruct, where the masonry shear walls were simulated using displacement-based beam column element with fiber section. Each fiber was assigned its corresponding material property. For the fully grouted masonry, the concrete model was used of Nader et al., and for the reinforcing steel, Meneghetto and Pinto material model was used. This modeling approach was validated against most of the walls available in the literature with different aspect ratios, configurations, vertical and horizontal reinforcement ratios, and also different axial stress levels. And you can see here that there was a reasonable agreement between the numerically simulated hysteretic response and the experimental one. And with this validated component model, it was integrated to a two-dimensional model utilizing the leaning column to account for the P delta effects. So the walls were assigned the displacement-based beam column elements, and the gravity walls were modeled using elastic beam column elements. Pushover analysis was performed to quantify the strength and displacement capacity of these studied archetype buildings, and these are 2 samples, for the one for the 20-story building located in Montreal, and the other one is for the 14-story building located in Vancouver. This table here summarizes the outcomes of the pushover analysis, emphasizing on the high period-based ductility of these studied archetype buildings. And then to gain more insight into the performance of these archetype buildings and to be able to assess the collapse capacity, incremental dynamic analysis was performed using 32 artificial ground motions, coming up to more than 1900 analysis runs to quantify the performance under strong ground motion excitations, which allows monitoring the structure's response from the elastic until collapse at increasing intensities. And these are again 2 sample IDA curves for the 20-story building in Montreal and the 14-story building in Vancouver. And summarizing all the IDA results, I come up with these 2 figures, which shows the impact of the increase in height given by the number of floors on the ACMR. And the ACMR is it stands for the adjusted collapse margin ratio, and it stands for the seismic collapse capacity. So a higher value reflects a higher seismic collapse capacity, and the standard that was used gives acceptable values. So for the buildings located in the high seismicity, all of them were pretty much higher than the acceptable values, and the same was for the Montreal region. So all the 6 archetype buildings, although they were violating the limits given by the code for the height, they had a very satisfactory seismic performance and a sufficient reserve in terms of the seismic collapse capacity. And with that, it was possible to conclude that ductile masonry shear walls with boundary elements proposed using the proposed hybrid structural system had an enhanced overall seismic performance and high seismic collapse capacity, reflecting the possibility of relaxing the height limits. So for the seismicity index between 0.35 and 0.75, we can go from 60 to 70 meter and even higher when more studies are there. And for the high seismicity, we can go from 40 to 50 and even more with future studies. Finally, the second phase, which was more on the depth of this type of structural system, having ductile and gravity shear walls looking at different configurations. So 12 archetype buildings were designed and studied to represent the mid-rise and high-rise buildings of 6-story and 12-story. The 6-story buildings had a rectangular configuration of the walls, and in confined is the walls with boundary elements. And for the 12-story buildings, it was only possible to use end confined or walls with boundary elements. Then the ductile shear wall ratio was varied. And the ductile shear wall ratio, it stands for the area of ductile shear walls in a direction divided by the total floor area. And the buildings were given a conceptual architectural layout representative of the typical construction of masonry apartment buildings. And it utilized obviously the proposed system of ductile and gravity walls. Ductile walls were given either a boundary element configuration or a rectangular configuration. And for the gravity walls, it was only a rectangular configuration with no seismic detailing. And the design was optimized over the height to come up with the most economical options for each building. And then again, a macro modeling approach was utilized, but this time in open seas to account for the shear flexion interaction using this new type of element, which is the multiple vertical line element model. And also it accounted for the strain penetration. So then the masonry, the fully grouted masonry was represented using the modified version of concrete model by Shang and Mander. And for the reinforcing steel, it was modeled using the model of Meneghetto and Pinto. And again, this modeling approach was validated against available walls in the literature and also the walls tested in this study. Similar to the previous one, it was integrated into a two-dimensional framework to account for the P delta effects. So the walls that were ductile were modeled using the shear flexion interaction multiple vertical line element model. And for the gravity walls, elastic beam column elements were used. After that, linear dynamic, nonlinear static, and nonlinear dynamic analyses were performed to come up with these relations between the ductile shear wall ratio and the peak interstory drift for the 6-story studied buildings and 12-story buildings. For the 6-story, we had two types of walls, rectangular walls, the boundary element walls, sorry, the red lines are the boundary element walls and the black lines are the rectangular walls. And for the 12-story, as mentioned earlier, it was only walls with boundary elements. And it was found that the trend between the ductile shear wall ratio and the peak interstory drift was maintained, whether it's response spectrum analysis, the linear dynamic analysis, or the nonlinear time history analysis. And the initial increase of the ductile shear wall ratio was the most effective in terms of reducing the peak interstory drift. After that, excessively increasing does not happen to be very influential in terms of controlling the peak interstory drift. Higher ratios were less influential. And then for the walls with boundary elements in the 6-story buildings, there was a reduction in the minimum required ductile shear wall ratio. So for the walls with boundary elements, it was 0.35, and for the rectangular walls, it was 0.7. So that's about 50% reduction in the required ductile shear wall ratio. Looking at the effect of the ductile shear wall ratio on the base shear demand, there was higher, obviously, base shear demand with the increase in the ductile shear wall ratio. But in this case, excessive amounts of ductile shear wall ratios remained influential in increasing the base shear demand, which highlights the need to decide the values based on the performance objectives, because it won't be really helpful beyond a certain value. And to optimize the design further of the walls with boundary elements, different alternatives was studied on how to reduce the size vertically. So starting, for example, at the first 2 stories of this size of boundary element, 400 by 390, going to 400, same size, and then suddenly stopping it or terminating it earlier. This is the 6th story. So either it's a constant throughout the height, or whether it's terminated after the 3rd floor. And then different alternatives for the 12-story, whether it's reduced gradually by 200, whether it's suddenly reduced to 200, then terminated, and another 2 alternatives. The effect was studied in terms of the influence on the profiles of interstory drifts. And you can see there was a sudden increase in the interstory drifts at locations where the boundary elements were either reduced or terminated. And the impact was also studied at looking at what's going on with the vertical strains at the end. There was sudden rise in the extreme fibers ends when the boundary elements were terminated, and there was also a shift in the critical section sometimes from the dynamic analysis. This was for the 6-story, and this for the 6-story building, similar observations. However, it was noticed that the option 3, which had the most gradual reduction in the boundary element size, was the least influential in terms of varying the peak interstory drifts and the vertical strains. So to conclude, at the system level, the proposed hybrid structural system of ductile and gravity walls optimized the design and structural performance of mid and high-rise masonry buildings. Relative to the conventional load-bearing structural system, the proposed layout of ductile and gravity walls reduced the required ductile shear ratio. Utilizing walls with boundary elements can even further reduce the required ductile shear ratio by up to 50% based on the example that was studied. And the choice of ductile shear ratio should be based on the performance objective. And boundary elements can be vertically reduced given that the reduction is gradual, it is beyond the plastic hinge, and a sufficient ductile shear ratio is used. Finally, this puts in the conclusion that masonry, when reinforced and properly designed, can be a competitive alternative construction material. So to just conclude with some quick design recommendations at the component level, some recommendations to increase the lateral resistance by increasing the concentrated reinforcement, and to enhance the displacement ductility, it is suggested to increase the confined end zone sizes. For the increase of energy dissipation capacity, it is suggested to increase the concentrated reinforcement. And utilizing C-shaped blocks instead of the stretcher blocks, it is recommended when constructing boundary elements of ductile shear walls in high-rise buildings. Special attention should be given to the shear resistance to account for the deformations, especially when having shorter shear spans to depth ratios. Lap splicing should follow the provisions of CSA because with that it was possible to overcome the bond failure and to reduce the premature bond failure. It is suggested to lap the rebars at the first floor and provide sufficient confinement, and this is only possible when utilizing C-shaped blocks. At the system level, it was concluded that to recommend the utilization of this proposed structural system, and with walls with boundary elements in this proposed structural system, it is possible to further optimize the design and improve the structural performance. The boundary elements can be gradually reduced, as mentioned, when we have a sufficient ductile shear ratio used, and also when we do this reduction gradually beyond the plastic hinge. So the reduction should be gradual beyond the plastic hinge, and the ductile shear ratios should have a predefined performance objectives. And finally, building height limits can be relaxed for ductile reinforced masonry shear walls with boundary elements. Thank you so much for your time, and feel free to ask any questions.